All right, let's talk about balancing redox reactions, balancing oxidation reduction reactions. And when we look at this redox reaction, it's unbalanced. It's not balanced. It appears to be balanced with respect to mass, but it doesn't appear to be balanced with respect to charge. You've got a +5 on the reactant side, +6 on the product side. So we need to make sure that both mass and charge are conserved in our balanced reaction. And the easiest method is to split the reaction up into the oxidation half of the reaction and to the reduction half of the reaction. So a half reaction is just an oxidation or a reduction. Oxidation is the loss of electrons. Electrons will be written as products in an oxidation half reaction, and electrons will be written as reactants in a reduction half reaction. We have a couple of specific steps that we're going to follow. So you just identify what's being oxidized and reduced, divide into the two half reactions, then just write down the compounds in each half reaction, balance each half reaction separately, and to determine the number of electrons transferred, and then you might have to multiply a half reaction to make the number of electrons lost equal the number of electrons that are gained. So electrons appear on opposite sides of the equations. Once you've done that, you simply add the reactions and you simplify the reaction and you check to make sure it's balanced. So here is a reaction. I've thrown nitrate in here. We can just sort of ignore that and just just eliminate the nitrate because the nitrate was the same in every specific case. So here is the reaction that was on the previous slide. It's in a very simplified form. We're not going to worry about oxygen in this reaction. We're just going to balance mass and charge of these ions. So we've got a +2 oxidation state over here for 10, and when we look over here, we see a +4 oxidation state. So this reaction is going from a +2 to +4 for 10, and that is clearly an oxidation. Electrons are being lost because the oxidation state of 10 is increasing going from the reactant side to the product side. So we call that oxidation. On the other hand, iron is going from a +3 to a +2. Its oxidation state is getting lower. That's clearly a reduction. And what we're going to do is we're going to split these reactions up into two half reactions. So we'll have the oxidation and we'll have the reduction half reaction. So for the oxidation, so we've got 10 2+, and the electrons are being lost because it's going to 10 4+, and that's a difference of 2 electrons, and so we have 2 electrons. Now, so far this half reaction is balanced. Mass is balanced with a 10 and 110 and 110 on each side of the equation. Charge is now balanced in this oxidation half reaction. We have a 2+ charge on the reactant side, 4+ plus 2 are negative charges. That is a total of 2+ on the product side. So this reaction, or this half reaction, is balanced. And then we'll do iron. So we've got Fe3+ on the reactant side, and over here on the product side, we've got Fe2+. And so we can see that one electron has been added to Fe3+ in order to equal Fe2+, iron 2+, over here on the product side. So we've added a negative charge to the +3. So this half reaction is balanced. But here's the problem. The number of electrons lost in the oxidation half reaction has to equal the number of electrons that are gained in the reduction half reaction. So we have to multiply the number of electrons by 2, and we can only multiply the number of electrons by 2 if we multiply the entire reaction by 2. And so now we have 2 irons, each one of them gaining 1 electron, So that's 2 iron, 3 pluses, gaining 2 electrons total, and 2 iron, 2 pluses on the product side. So we've got 2 times a 3 plus, which is 6 plus 2 times a minus 1, that's a 2 minus, plus a 6 plus makes 4 plus, and 2 times a 2 plus is 4 plus. So the number of electrons that are being gained by iron 3 plus are equal to the number of electrons that are being lost by 10 2 plus to equal 10 4 plus. So now that we've done that, we can go ahead and we can cancel the number of electrons, and we can simply add the result for the balanced reaction. That'll give us 10 2 plus 2 iron 3 plus, and then we'll make 2 iron 2 plus 1 10 4 plus. Now we'll compare, or we'll check to make sure that the reaction is balanced. I have 110 and 110 over here on the product and the reactant side. And then I have 2 irons, so mass is balanced, mass is conserved. We've got a 2 plus 2 times a 3 plus, which is 6 plus 2 plus, that's 8 plus. Here we have 2 times a 2 plus, that's 4 plus another 4 plus, so we have 8 plus on the product side and 8 plus on the reactant side. So we have balanced both mass and charge. Here is just the summary of what we just did. We started out with this reaction. We figured out what was being oxidized. That was the 10 2 plus to 10 4 plus. What was being reduced? That was the iron 3 plus to the iron 2 plus. And we just split the reaction, the oxidation half. This was the oxidation half reaction. This was the reduction half reaction. We figured out the number of electrons gained, the number of electrons lost. Then we had to multiply the second equation, the entire equation, by 2 to get the number of electrons gained to equal the number of electrons lost. They have to be the same on both sides. Once we did that, we simplified by canceling the number of electrons. I seem to have done it here after I added the reaction. You can do it either way. The number of electrons on each side have to be equal. You have to have an equal oxidation and reduction. So both mass and charge have to be balanced. So let's take this little quiz. Let's figure out how many electrons are transferred in the following reaction. Now, to figure out the number of electrons transferred, you have to look at the oxidation states. Here's hydrogen in its elemental form. It has a 0 oxidation state. This is H+, and monoatomic ions, they get their charge. But here's what you want to realize. You've got a 2 times a +1 here. That's +2. The charge on the reactant side is 0, so you need 2 negative charges in the form of 2 electrons to neutralize the 2 positive charges in the form of the 2 hydrogen ions, each with a +1 charge. So 2 electrons are being lost in this oxidation reaction. How could I tell it was an oxidation reaction? We went from a lower oxidation state to a higher oxidation state. And if you're just looking at the half reaction, the electrons are on the product side, which means that electrons have been lost. So the answer here was 2 electrons have been transferred. So let's balance the following reaction. Let's figure out how many electrons are transferred in this reaction. So here is that reaction. So first of all, let's take a look at fluorine. This is diatomic fluorine. It's in its elemental form. It has an oxidation state of 0. This is iron 2+. It gets its charge, its oxidation state. And that's going to be true for any monoatomic ion. It's the same as the charge, the oxidation state. This is fluoride ion. That's a negative charge right there. So its oxidation state is -1. Here's iron 3+. It's got an oxidation state of 3+. So fluorine is going from 0 to a -1 oxidation state. Its oxidation state is getting lower, and so that's going to be a reduction in oxidation state. So reduction. And then we have iron going from a 2 plus to a 3 plus, and that's going to be an oxidation. Next thing we do is we split the reactions up into their half reactions. You could put oxidation first. I tend to put oxidation first. You could put reduction first, but as I said, just habit, I do oxidation first. So let's do the oxidation. So I've got Fe 2 plus, and I'm going to Fe 3 plus, and that's going to give me 1 electron over here, or some number of electrons. We'll figure that out in a second. Let me do the reduction half of the reaction. That's going to be fluorine, diatomic fluorine, and if it's a reduction, that means there's going to be some number of electrons on the reactant side that are added, and that's going to give me the fluoride ion on the product side. So there's my reduction. So let's balance the oxidation half first. So we're going from 2 plus to 3 plus. That is the loss of 1 electron, so that'll just stay as 1 electrons. I've got 1 iron and 1 iron. So mass and charge are balanced so far. Here, I've got 2 fluorines on the reactant side, only 1 fluorine on the product side, and so I'm going to go ahead and multiply the fluorines on the product side by 2. Now mass is balanced. I have 2 fluorines and 2 fluorines. Let's figure out how many electrons we need. Well, I have a 0 charge over here. I have 2 negative charges on the product side, and so I need 2 negative charges added to the 0 charge that's on diatomic fluorine here to have a 2 negative charge over here on the reactant side as well. So mass, I've got 2 fluorines, and charge, I've got 2 negative, 2 negative. Mass and charge are both balanced in the reduction half. Now we need to get the number of electrons equal to each other, so I have to multiply this entire reaction by 2. That includes the electrons to get the electrons to balance. And so let's check it out. I've got 2 irons, 2 irons. I've got 2 times a 2 plus, which is 4 plus, 2 times a 3 plus, which is 6 plus 2 negatives gives me 4 plus. So mass and charge are balanced. So now I can go ahead, cancel my electrons. I know that I have 2 electrons lost in the oxidation, 2 electrons gained in the reduction, and I can simply add my reactions together. So that's going to give me 2 irons. That's 2 iron 2 pluses plus fluorine, diatomic fluorine, and then I'm going to get 2 fluoride ions plus 2 iron 3 plus ions. I'm going to just check, make sure that everything is balanced. I've got 2 irons, 2 irons, 2 fluorines, 2 fluorines. I've got 2 times a 4 plus is 4 plus. 2 times a 3 plus is 6 plus 2 times negative 1 is negative 2, plus 6 plus is 4 plus. So I have a 4 plus on this side and a 4 plus on this side. Both mass and charge have been balanced. So far I've kept the balancing of redox reactions very simple. We just wanted to figure out how many electrons were being transferred and how to get mass and charge balance. But let's say you have full-on compounds or polyatomic anions where oxygen is involved. So there's lots of oxygen-containing compounds around because oxygen is everywhere and it gets in everything. Look at rust, Fe2O3, this guy sitting right here. So you get some iron, and as soon as you get iron in an oxygen atmosphere, it's going to oxidize. You're going to get corrosion, which we call rust. It's common redox reaction. Combustion reactions are redox reactions. So often the compounds on the other side of the equation have different numbers of oxygens in the formula, and so we're going to use the same half reaction method to balance redox reaction, but it has a few more steps. So the difference is balanced by adding water to the side that requires more oxygen and hydrogen ions or hydroxide ions, depending on whether we're balancing under acidic conditions or basic conditions. So we're going to balance under acidic conditions, and I'll show you exactly how to convert that to basic conditions. It's really pretty easy. So here is a reaction. The instructions are actually posted on tracks, but we're going to go ahead and go through the process. So the first thing you do is the same thing you did before. You've established the oxidation states of all the elements. So step one, we're just going to assign oxidation states. If you've forgotten how to do that from the first, go look at the first video. We've got a -2 charge on oxygen. It gets its charge 3 times the -2. -6. The overall charge on the nitrate ion is -1, so the -6 has to add up to something, some positive charge to give you -1, and that's going to be +5. Over here we've got a monoatomic ion, that's copper, and it's 2+, so it's got a 2+ oxidation state. And here we've got nitrogen dioxide, a molecule, so all the oxidation states have to add up to 0. 2 times a -2 is -4, so nitrogen is going to be a +4. All right, so copper is going from 0 to +2. That's clearly oxidation. And nitrogen is going from +5 to +4. That's a reduction in oxidation state. So let's split them up. So let's do oxidation half reaction and reduction half reaction. So the oxidation state half reaction is Cu going to copper 2+, and let's go, and we have a little bit different technique for this. So let's go ahead and write the reduction half reaction, and the reduction half reaction is nitrate ion, and it's going to, we know we're going to be adding some electrons here. We don't know how many, so we're going to hold off on that. And then over here we have nitrogen dioxide. All right? Okay, so here we go. The first thing you want to do is balance the elements other than hydrogen and oxygen. So I got 1 copper, 1 copper. So that's done in this particular case. This one was pretty simple. The next thing you want to do is balance the oxygen atoms by adding water to the side with fewer oxygens. Well, we don't have any oxygen in the oxidation half reaction, so we don't have to worry about that. Then you balance the hydrogen atoms. If you need to balance hydrogen atoms, we don't have to do that either for the oxidation half reaction. Finally, we're going to balance the charge by adding the number of electrons to get the charge to be the same on both sides. This is a 0 oxidation state. This is 2+, so we add 2 electrons. Okay, so we've balanced mass, we've balanced charge. We didn't have to worry about oxygen. We didn't have to worry about adding hydrogen. So this oxidation half is done. This is going to be a little bit more complex. So if you notice, we've got more oxygens on the reactant side than we do on the product side. So first thing we're going to do is we're going to balance all the elements other than hydrogen and oxygen. So let's go ahead and do that. We've got 1 nitrogen and 1 nitrogen. So far, so good. Let's go ahead and balance hydrogen or oxygen and then hydrogen. Well, we've got 3 oxygens and 2 oxygens. So I need another oxygen over here on the product side. And that's going to be by adding water. So that's what you do. You add water to balance the number of oxygens. Now I have 1 oxygen plus 2, that's 3, and I have 3 on the reactant side. But in the process of adding water, I've also added a couple of hydrogens over here. So I need to add 2 hydrogens over here on the reactant side in order to balance the number of hydrogens, 2 hydrogens, 2 hydrogen. Finally, I need to balance charge by adding enough electrons to get the charge to balance. Now, if I look over here on the product side, I have a neutral molecule and a neutral molecule, so I have 0 charge. So my charge has to be 0 over here. Well, I've got 2 plus 1 charges from the hydrogens and a negative 1. That adds up to plus 1, so I need to add 1 electron on the reactant side. So now I've got both mass and charge balanced in the reduction half of the reaction. What I need to do now is what I did before, is I need to get the number of electrons the same. I have 2 electrons for the oxidation half, only 1 electron on the reduction half, and so this entire reduction half reaction needs to be multiplied by 2. So that's going to give me 4 hydrogens plus 2 nitrates plus 2 electrons, and that's going to make 2 nitrogen dioxides plus 2 water molecules. Let's just make sure we're still balanced. I've got 4 H pluses, and here is 2 times 2, that's 4 hydrogens. I've got 2 nitrogens, and I've got 2 times 3, that's 6 oxygens, and I have 2 times 2, that's 4, plus 2 times 1, that's 2, 6 oxygens. So that's mass. Mass is balanced. Let's go ahead and make sure charge is balanced. I've got 4 times a plus 1, which is plus 4, plus 2 minuses, plus 2 minuses. A plus 4 plus a minus 4 is 0 net charge, same as the product side. So both mass and charge are balanced. So we're going to go ahead and I'm just going to erase. You would just probably scratch this out. This is now my balanced reduction half reaction. I'm going to go ahead and I'll cancel the electrons. So I'm simply going to add these two together. So that's going to be 4 H pluses plus 2 nitrates, and then that's going to be plus copper metal. That's a solid. That's going to give me copper 2 plus 2 nitrogen dioxides plus 2 water molecules. Let's just make sure mass and charge are balanced. So let's make sure that mass is balanced. We've got 4 hydrogens, 2 nitrogens, 2 nitrogens, 1 copper, 1 copper. Let's check the oxygens. 2 times 3 is 6, 2 times 2 is 4, plus 2 times 1 is 2, that's 6. So mass is balanced. So mass balanced. Let's check charge. We've got a 4 plus a 2 minus gives us a net 2 plus charge on the reactant side, and I have a copper 2 plus and 2 neutral molecules. That's a 2 plus charge on the product side. So charge is balanced. So this reaction is balanced under acidic conditions. Balanced in acidic conditions. And you can tell that because you have an excess of hydrogen ion that is in this particular solution. The excess of hydrogen ion, that makes the solution acidic. So these are acidic conditions that you've balanced this redox reaction in. So what we're going to do next is I'm going to show you a really simplified way to balance this very reaction under basic conditions. So we just balanced this reaction under acidic conditions. Now we want to simply convert it to basic conditions. Well, how do you convert a reaction from acid to base? You add hydroxide, and that's exactly what we're going to do. So we've got 4 hydrogen ion over here on the reactant side. So what we're going to do is we're going to add 4 hydroxides over here. And if we add 4 hydroxides on the reactant side, we have to add 4 hydroxides on the product side of the reaction. So here's what happens when we add the 4 hydroxides. 4 H pluses plus 4 OH minuses make 4 H2Os. And then we've still got our 2 nitrate ions with a -1 charge. We've still got our copper over here. And now we have 4 hydroxides. And we have our copper 2+ ion. We've got our 2 nitrogen dioxides. And then we also have 2 water molecules. So now our solution has an excess of hydroxide ion. It is in basic solution, but we need to cancel anything that can be canceled. So you'll notice that I have 4 waters on the reactant side, 2 waters on the product side, so I can cancel 2 of those water molecules. So I can make that 2. I'm done, but let's compare. Let's make sure that we're balanced on everything. So I've got 2 nitrogens, I've got my 2 nitrogens, I've got my 1 copper, my 1 copper. Let's go ahead and balance hydrogen. 2 times 2 is 4. I have 4 times 1, that's 4 hydrogens. I have 2 times 2 oxygens plus 2 times 3, that's 6. 6 plus 2 is 8 oxygens. I have 4 oxygens here. 2 times 2, that's 4 oxygens here. And so my reaction is balanced. And because I have excess hydroxide ion, I am balanced in basic conditions. Let's just check charge to make sure that charge is balanced. I have 2 -1 charges over here. I have 4 -1 charges on the hydroxide ion, but I got a 2+ on the copper 2+, and so I have a 2- charge here and a 2- charge here. So I am balanced under basic conditions. So all you do, my suggestion is balance under acidic conditions and then just add enough hydroxide ion to neutralize all the hydrogen ion that's in excess in your reaction. So if it's 4 hydrogen ions in excess, you just add 4 hydroxide ions, and that will balance you out.